All right, so I hope it's 4:35. We can start. People will be joining in the meanwhile. So for those people who have joined, welcome. Um, Aqib, welcome to you as well. Thanks for accepting my invitation and joining this session. I first introduce this CS learning series, what this learning series is about, and then I will introduce this today's speaker. So CS Clinic is basically an initiative at the Smart City of Technology to introduce the hands-on project experience for early years and for CS students in early years. So the basic idea is that we should provide the exposure to students to introduce and learn about the projects and about the hands-on skills by project-based learning or by implementing different projects before starting the final project. We successfully graduated first batch this year, and these students are now working on some fantastic project idea in their final year project. Uh, Today's in order to actually achieve this step, one of the series is the learning series. So it's not only about to get students on the project; it's about to introduce them about the latest technology, research, what's going on in the world. So this is the basic idea. So this is today's lecture is also the part of that series. Um, so today's speaker is Aqib Saeed. Aqib Saeed is a PhD candidate in the University of Eindhoven, University of Technology in Netherlands. The Aqib is my access student. I taught him data structure, if I'm right, in Ph.D. Probably around 4, 5, 6 years back. If I remember correctly. So Aqib is about to finish his PhD. As I am expecting, and I was reviewing his work, and as I was expecting, Aqib is an exceptional student, and so his work is also exceptional, pretty good. I will request you people to check his website, take his homepage, which is aqibsaeed.github.io, and learn about the latest work he is doing. So Aqib, now the floor is yours. You can start your presentation.
Thank you very much for inviting me. Thanks for having me. Can you guys see the screens fine? I guess yes.
Yep,
so then I can start. So I will try to also speak in Urdu a little bit. So I will give you an overview of my research, but more broadly about self-supervised learning, or to put simply, how we can build systems that can learn without a lot of human intervention, or like without a lot of label data. So this will bring us to the topic of self-supervised learning. So we all know or like heard of the success of deep learning methods, and most of us like heard about object recognition or language modeling like GPT-3 or BERT, or agents that play Atari games at human level performance, or I guess most of us like definitely heard of game AlphaGo, or which basically beat the world champion. And so behind all this success are basically deep learning methods, or like methods that can learn directly from data without any human intervention in terms of developing features. So to make these things even more concrete, let's say we want to classify image of car, or we want to recognize if there is a car in an image. So how we can do that? So in the early days, before the success of deep learning or neural networks, what people used to do, they used to extract or handcraft features. For example, they look at how the car's tires look like, or the car's windshield look like, or stuff like that. And then they extract features from it, and then they will feed it into some sort of learning algorithm, or you can say a black box, and that will tell the human if there is a car in the image or not. But the problem or the limitation of this method is that you need to come up with features that are really good at describing what is going on in the image. And that is a really hard part to do. So what happens with deep learning or with deep neural network is that they learn these features automatically from the raw image or from the raw input. So there is no human involvement in that part of the modeling. But the thing is that we need access to label data sets. And there are three factors behind the success of deep learning. One is that we now have better algorithms or better understanding of existing algorithms. We have large compute available, like we have better GPUs, we have better TPUs for training these models. But most importantly, we now have access to large scale data sets. So the data set that we have, they are all well labeled by the human annotators. For example, you can go on Amazon Mechanical Turk and you can ask thousands of people all around the world to label images for you or to label audio clips for you. For example, who is singing in this song? You can ask this type of questions. The human annotators are going to listen to those songs and then they are going to assign the labels. Same goes for images and same goes for other modalities, for example, line views or ECG or EEG. But the thing is, and the most important thing is that, as I just described, that you need to have large-scale data sets for training these models. And this is really a limitation. This is not how humans learn in general. For example, if I show you the picture of a basket or some mobile phone only once, then you will have like this concept of a smartphone or a basket. And then if I show you some other type of smartphone or other type of basket, you can always recognize between these two. You don't need, or like as humans, we don't need like thousands or millions of images to learn about some concept. But these deep neural networks, they need access to like millions of images or large scale data set to learn like really what's going on in those images. So for example, if we look at really state-of-the-art models that are trained on ImageNet for object recognition, they are generally or mostly trained on millions of images, or the ImageNet data set is the public data set, or the other Tencent ML image data set, it has like around 17 million plus images. So people generally use these data sets, and internally within big companies like Google, Microsoft, or Facebook, they have their own data set, which goes towards the size of like billions of images. They are well annotated, and then they can train their models on such data sets. And same goes for speech recognition systems. So speech recognition systems like Siri or like Google, OK Google, or stuff like that, they all are trained on 1,000+ hours of annotated data. You need to have access to very well annotations from diverse regions, from all across different countries, to have a system that works well for everyone. And then there are systems like AlphaGo, which basically beat the world champion on the game of Go, and no one really knows for sure like for how many hours this model was trained for. So now we know that these models, they work very well as compared to manual handcrafted feature engineering, where humans sit down and take a look at the features that are most distinguishable for the task. And but the thing is that they need data at scale. And now I will talk about why these labeling is very difficult to do in practice. So I'm going to list down these points, and then we will know, or we will appreciate this point, that why we need to develop methods so that we can learn from unlabeled data automatically. So the first thing is granularity. So if we want to ask human annotators to label the data set for us, then we need to define some classes or hierarchy for them to be labeled. Like for example, if we want to classify between animals and vehicles, then should we classify all animals and all vehicles into two classes? Or should we go on and divide animals into further hierarchy like carnivorous or herbivorous, and then go on like cats, dogs, or some other stuff? And the same goes for vehicles as well. So do we need to classify everything like aeroplanes or cars and everything into one category, or do we need to refine them? So there is this boundary is not very clear, and this granularity could be like very difficult to specify. Thing is, for which task or problem should we assign labels to? And for example, if we ask human annotators to label the data for us, for the lamps that are in Paris, for example, and the doors also, or windows that are in Paris, then this model generally, if we train some model to recognize these three things, and then we take this model to some other place, for example, let's say Pakistan or India or Bangladesh, or I don't know, maybe in England, then that model does not really work relatively well. And then we need to again collect some data that is representative of the surrounding in those countries, and then we can have a reasonable performance. So it's not really clear for which problem or for which task we go on and collect the label data. And then there are problems like segmentation or bounding box detection, and these annotations could be really expensive, and even human annotators like take 3-4 minutes to label one image or even more. Then there is an aspect of privacy. For example, in the mobile phones, there are keyboards that they can predict the next word that you are going to type. And if you want to have like label data related to this or banking or finance or insurance, and we are asking someone to look at your data and then label it, then this could be like really bad from the privacy perspective. And then there are things for which you need really expert level knowledge. Like for example, you need to be a doctor, you need to be like an expert neurosurgeon to basically look at the image and then specify if there is something wrong going on with that person. For example, in the chest X-ray or with the retina of the eye. So we need expert level knowledge for labeling such images. So we asked this question, that is it possible that we can learn semantic representations from the data that could be image, audio, or other type of signals without relying on strong labels, so that we don't need to like specify, for example, in this case, okay, like there is something wrong going on, or there is something wrong going on, or there is something wrong going on. So the answer is, can we use the data that we have, like images or audio or some other signal, so that it can provide its own supervision, so that we can extract supervision from the data itself, and then we can use existing algorithms or we can develop new algorithms. But then we don't really need to rely on semantic labels for the task. And this will bring us to the topic of self-supervised learning. But I want to clarify one thing, is that there are several methods for unsupervised representation learning. But in this talk, we will look at one particular type of unsupervised learning, which is self-supervised learning. And the thing is, it is a form of unsupervised learning where we don't need access to the label data. We can learn the general purpose useful representations that transfer across the task. For example, if we learn these representations from data set A and then we take these representations to some other related data set, then these representations generally work very well. And the thing is that why we need it, as I explained earlier, that large unlabeled data sets are very easy to curate. Like we can download such data sets from the website, or like we can scrap them up, or we can ask someone to provide us such data sets that are unlabeled. That is generally easy to get as compared to supervised data set. And the thing is that, as I mentioned earlier, for example, with medical imaging or with other signals, those domains are supervision starved because you need expert level knowledge to basically label those images. So the key idea in self-supervised learning is that you need to basically formulate an auxiliary or pseudo, or you can say a proxy task for the network to solve, that basically does not require any manual annotations from the human, but that basically necessitate the semantic understanding of the image or of the other data modality. So to put things into perspective, let's say the example of self-supervised learning is that you have this image of a cat. We can divide this image into different patches, and then we can ask a neural network to basically predict where this patch will go. So for this type of self-supervised task or for learning representations, we don't really need access to the label data. We can split a single image into different patches. We need to be careful. I'm not going into details, but we can divide this image into different patches, and then we can ask the network to predict the position where each patch will go. And it's somehow sort of like solving a jigsaw puzzle. So that if we have like millions of images that are unlabeled, we can automatically, through the code, we can generate semantic labels, and then we can solve these type of tasks, and we can learn useful representations. And for that, we don't really need access to the label data. Another example is, let's say you have a black and white colored image. We can make it grayscale, and then we can feed in the grayscale image into the model. which could be black box for you, but then we can ask the network to produce a color version of the image. So this could be another task. And for this task as well, we don't really need access to any type of label data. Same goes for in painting. Let's say you have an image and then you take a patch out, or you make it black or white, and then you ask the network to basically reconstruct like what's behind this particular patches. So there are like different ways, like if we ask human artists to create it, this is how it looks like, and this is how it looks like with the state of the art. Like it's not really state of the art right now, but it was in 2016. Now things are much better, and this is how it looks like. So this could be another self-supervised task or auxiliary task. What if you have videos? How you can learn? If you have a video, you can, for example, ask the network to detect if these frames are in a particular order or not. You can do order verification. Same goes if you have videos recorded from two different views, then you can ask the network, are these two views related to each other or not? So in the views shown by the blue boxes, they are related to each other. But if we compare this blue box with this red box, then these are not really related to each other. They belong to a different setting. So we can also ask the network to basically learn from these type of two different views. Then if we have audio visual data, let's say we have some video along with the audio, then we can feed in the video frames and we can slightly shift the audio a little bit. And then we can ask the network if this audio is synchronized with these video frames or not. So this is a really simple self-supervised task, and it works really well in practice as well. But there could be a question that, okay, if we have these video frames and I put the video or I put the audio from some other video, then it's going to work. Then this is not really a good self-supervised task. Network will find a way to cheat and learn really non-useful features. So the thing is, we need to keep the same audio but slide it a little bit in time, and then ask the network if these two modalities are synchronized or not. And this is a more recent work. For example, if you have an image X or some other data modality X, we apply two different type of transformation, which are represented by T here. We expect some representations H, which would be very high level features, how the network sees X. And then we can ask the network to maximize the agreement. So let's say you have an image of a car, which will go here, and you will apply some transformation. Let's say you make it grayscale, or you rotate the image of car a little bit, and we feed both of these images into a neural network. We get the representations, and then we pass them again through another neural network G, and we get Z, and then we ask the network to maximize these representations, because these representations belong to the same object. But because we will be feeding the other images as well, for example, here will go the car or will go some other object, then the network is not going to maximize the agreement between those two objects. And for these type of self-supervised tasks, we don't really need access to the label data. So far, we have seen that there are many ways to learn representation from images and from videos, but what about other modalities? Or what about other sensors that we are surrounded by and that are producing EEG or ECG that monitor your heart rate, or IMU, for example, accelerometer or gyroscope in your mobile phones, in your smartwatches, or what about audio? So now I will talk about my research. I focus on sensory representation learning. And I'm going to list down several self-supervised tasks that are specifically designed for learning from, you can say, time series or any type of 1D signal. So the one thing could be is we can have a model which we train to recognize different transformations or different ways of altering the signal. So let's say we have a clean ECG signal or an accelerometer signal as shown here. In this case, we apply some type of transformation, which would be like adding simple noise or permuting the signal, or like making it shuffle like this from left to right or right to left. And we apply these transformations on the signal, and the data is completely unlabeled, as I mentioned earlier. And then we ask the network to recognize if there is some type of transformation applied on the input signal or not. And for this self-supervised task, you don't really need access to any type of labels. The data will be coming in all the time from your smartphones or smartwatch or some other type of device, accelerometer. We apply these type of transformations, and because we apply these transformations ourselves, we know the labels as well. And then we ask the network to solve this task. And once this pre-training phase is done, then we ask the network to, we basically freeze these network. By freeze, I mean that we keep this network fixed because it is learned. We are not going to change it in any way. And then we ask the network to solve the end task or downstream task which we are interested in. For example, we can recognize what the person is doing. If the person is biking, he or she is in a car, or if he or she is sitting or walking or running, stuff like that. So this could be like one very simple and intuitive self-supervised task for learning from time series or sensory data set. And you can apply these type of transformation on any type of signals. The other thing is, there are different type of signals where you can say that, okay, maybe if I will apply this type of transformation, then they are going to distort or they are going to destroy the pattern in the input, and we will not be learning anything useful. So can there be another way of learning representations? So then we come to this task of contrastive learning, or you can say comparing. If we have this type of signal, we extract another representation from it. Like, for example, we apply Fourier transform or wavelet transform on the existing signal. So we have a different representation or different view of the signal. Then we ask the network to basically recognize if this raw signal produce this scaleogram or not. So the idea is we have corresponding views of this raw signal, and then we ask the network to basically check if this signal produce this scaleogram or not, or vice versa as well. And then for this task as well, we don't really need access to any type of labels. And here, for example, we can have ECG coming in, and here we have a scaleogram, or when we apply wavelet transform on it, we extract some type of scaleogram, this visual representation. We feed this in, and then we can have contrastive loss on top, and it can learn it can basically train these two pipelines to learn good representations. And once we learn this representation, we discard this entire pipeline, all this part, we just keep this signal subnetwork, and we use it for downstream evaluation in the same way like we did here on this slide. All right. Then there we can ask, like, could there be other more simple way of learning representations? Like, instead of doing transformations, or instead of going into generating more corresponding views, which would be really difficult and expensive, both in terms of tooling and implementation on the resource constrained devices, like, for example, smartwatch or your smartphone. Can we develop some other self-supervised tasks so that we can use them on the device? So I did this work at when I was in Google with my collaborators. So we developed several self-supervised tasks, and we study this phenomena. You can go and read more about it here. I will just highlight a few of the auxiliary tasks that we developed, that you can really develop that sound very simple auxiliary tasks, and then they can learn and then you can show that basically they learn very meaningful representations, or to put simply, that they achieve very good performance on the task that we are interested in. For example, activity classification, or sleep state scoring, or estimating your heart rate and stuff like that. And the one task I can explain, for example, the estimating features from masked window. And the thing is that generally people extract features from the data, as I explained in the beginning of the talk. So what we can do, if we have a 1D signal, we can mask some aspects of the signal, we can mask some aspects of the signal out, but before masking them up, we can extract some manual features from it, as some humans do. Then we feed that masked signal into the model, but we ask the network to predict those missing or masked area. But on a more higher level, we ask it to estimate those features that we extracted. And we noticed that this simple task able to learn feature that is basically takes our model with in performance which is equivalent to fully supervised model that is trained directly when we have access to all the labels for a particular task. So the idea is again is simple, like we can have signals coming from any of these devices. And let's say we selected accelerometer and gyroscope. We feed in the label data. We have a self-supervised data generator here, which correspond to any of these auxiliary tasks. We have some network which you can consider that it is a black box for you. But we feed this data in. We do the pre-training. In this phase, once this phase is done, we discard all this, but we keep only this temporal convolutional neural network, which is shown here. And then we feed in the label data. We don't train this model. And then we can show that we can get this really good performance even in with few label data points. Let's say when you have only 5 or 10 label instances for each class. So it is really good as compared to when you need millions or like 100,000 different examples for each class. And this is how it looks like, say, if we try to write it in pseudo or more algorithmic way. I will not go into detail, but the idea is somewhat similar to what we saw here. We have a pre-training phase going on here, and then once our pre-training phase is done, we can randomly sample a batch of label data, and we can directly learn a classifier on top of these representations that we have. I will try to show like very cherry-picked results. So these are like different type of data sets that are publicly available. We used, and then they are mostly related to activity recognition, but we can do stress detection in a person using their heart rate signal if the person is feeling stressful. We can detect what the person is doing from the Wi-Fi CSI information coming out of the Wi-Fi routers. We can detect if the person is sitting or if the person is walking and stuff like that. And we can do much more fine-grained activities if we have access to accelerometer and gyroscope from a smartphone. And on a very high level, you don't need to look into these numbers. There are a lot of numbers, I understand, but the key idea is that if you have a fully supervised model, which and it basically scores these numbers on different data sets, which you can say like if we are close to 1, we are good. If we are close to 0, we are doing really bad. So these are the different numbers here when we have access to the label data. And we can see that if we train our model with self-supervised task, which does not have access to any label data, we freeze the model as I showed earlier. And then we train only one layer on top, which is related to solving that particular end task, for example, activity classification in this data set. Then we can see that sometimes we perform even better as compared to fully supervised model. And same goes on the other data sets as well. And here, for example, so you can say that, okay, like these all data sets are related to accelerometer and gyroscope, but in this case, we were using EEG to recognize the level of sleep, you can say, or sleep state scoring, to put it more formally, so in which stage of sleep the person is. And then on this data set, you can see that we are able to recognize if the person is feeling stressful or not during driving. And you can see in this case as well, our self-supervised models works really well as compared to the fully supervised model. And we can say that this self-supervised model learns more general representation as compared to if we directly try to solve this particular task, which is stress detection. And these are more like really some cherry-picked results, you can say, when we have when we pre-train our model on unlabeled data, but now we have very few labeled data points. Let's say for solving this task on for activity recognition, we have only 5 label instances. The fully supervised model gets 60% accuracy, you can say, but this model will go on with trained with self-supervised model will give us 5% more improvement. And improvement in some other cases are even more significant. And so this is another way to look up if the model is learning something useful. So we can produce these type of visualizations where we can see, okay, if the data points, so each of these points belong to one image, you can not like image to belong to one instance, But if your understanding instance is difficult, you can think that this one data points belong to one image. So if these data points are closer to each other and they are forming nice clusters, it means that the network is doing really well in learning useful representations. So, but the interesting thing is that we learn these representations in a completely self-supervised way. So there are no labels provided to the model about, for example, if the person is falling down or walking or standing up, model discover these categories automatically. So all these labels are basically added post hoc after doing the learning to basically try to understand, okay, if these points are belonging to one particular class or one particular cluster. And we can see that in most of the cases, all these different classes are forming very nice clusters. For example, if the person is cycling, then they have their own nice cluster here. If the person is standing, they have their own nice cluster here. Same goes for sitting. But we can notice an interesting thing which is going on here with walking upstairs and downstairs. So one can argue that, okay, going upstairs or downstairs is also a walking. So there's really no difference between this, but you can see that they are very close to each other, which makes sense as well. And then we can also look at, if we have this type of accelerometer signal, we can basically combine these three axes. So there are generally three signals you can say that coming out from an accelerometer from any device. We merge them up, so we will get one nice representation. This is a magnitude. And then it is just done for better understanding. And then we can look at where the model is looking when deciding for a particular class. So if the model is saying that the person is going downstairs, we can ask this question, okay, we know that for sure that the person is going down because we have access to the label data. We know that the person was going down stairs. Then we look at where the model looks when we train the model directly with the labels. But we can also look with a self-supervised model where it looks. So if these two models are looking at on the same positions or on the same aspects of the input signal, then we know for sure that, okay, they are doing the same thing. So we don't really need access to the label data. So this is another way of like interpreting these models, like where these models are looking at. Now I will talk about, so far we saw that we can learn these representations from ECG, from EEG, from IMUs, or from other type of signals. But what about audio? So there is a lot of work done in audio, unsupervised audio representation learning. I will talk about my work only. If you are interested in other references or citations, you can go and read my paper. But we are like state of the art on a lot of benchmarks, and I'm going to show you the results. So the key idea is that, let's say you have large scale unlabeled audio data set available. So how we can learn representation from that. So generally people mostly focus on speech representation, like, so you can say how you can differentiate between an audio and speech. So the speech could be any audio, like for example, you giving a command to Siri or Alexa, but there could be a different type of audios, for example, sound, music playing in the background, or there is some car going on outside, like acoustic scenes. If I'm at an airport or some other place, of example, there is a dog barking or some other animal sound detection. So they are not related to speech. So most of the work done in this area is related to speech, but we wanted to, and there is very little work done in unsupervised learning on learning more general representation for any type of audio. So that's why we were more interested in learning general purpose representations. And then these are more like technical details, how existing methods do, and our method does not really depend on these type of stuff. So we don't really need to like go into this detail, but on a simpler level, if I try to explain it to you, let's say you collect large number of audio clips, which looks like this. If you try to plot them, we expect 1 second segment from each of the audio clip, and then we expect some high level representation manually from it, which are called, you can say, spectrograms. And then we feed in those 2 clips extracted from the same audio clip into the model. And then we ask the model to maximize their agreement, if they are coming from the same audio clip or not. But the other thing that you can do, you can add a little bit of noise in this audio clip as well that you extracted from this larger audio set. And once this pre-training or self-supervised learning phase is done. So the self-supervised learning in this case is that you ask the network to verify if this clip and this clip, they are both coming from the same audio clip or not. So this is the self-supervised task. It's very simple, and we try to maximize the agreement. There are a lot of technicalities, but I'm trying to say if you think of it on a higher level, it makes intuitive sense. If you ask the network, if you take two patches or two segments of 1 second or more than 2 seconds, and you ask the network if they belong to each other or not, then you can learn useful representation. So when this self-supervised pre-training is done, then we can focus on our actual task that we are interested in. Now we are going to look at that. So we use AudioSet. This is the largest publicly available data set available. It has 2 million plus audio clips, and we use it as an unlabeled data set for this pre-training phase to learn general purpose representations. Once that thing is done, we go on and evaluate this model in a completely different setting on completely different data set that the model has never seen during the learning phase. For example, for differentiating between music, if the music is playing in the background or there is a noise coming or if there is someone talking, then we can also recognize who is speaking. For example, we can identify the speaker, we can recognize acoustic scenes. If the person is in the grocery store, if the person is at the airport and stuff like that, we can also detect we can do keyword spotting. Like for example, you giving a command to the Alexa, Siri, or to your light bulb, where voice like turning the bulb on and off and stuff like that. We can detect which language the person is speaking, German, English, and stuff like that. We can even classify which instrument is playing in the background. So we can show that our model works relatively well across different type of tasks. These are again the same things that I explained earlier and a bit more technical, so we can skip that, but the high level idea is same, that we pre-train our model or we do self-supervised learning on AudioSet, that is the largest publicly available data set, in a completely unsupervised way without using any labels, and then we transfer that model to the other tasks that we are interested in solving. So these are the results. So if we take a fully supervised model that is directly trained on this data and with the task specific labels, for example, in this case, speaker ID, then we get these type of performance. On average, we get 83% accuracy. But if we pre-train our model, which is called COLA, contrastive learning for audio, and we pre-train it on AudioSet, but then we go on and fine-tune it on these downstream or n task data set, then we improve the performance 2% on average. And on some tasks, the performance is even significant. For example, if we look here on speech commands, we improve the performance 1%. If we fine tune, then we improve the performance from 71% to 98%. And same goes for other tasks as well. Yeah. And then we compare our method with the existing work. I'm not providing citations on this slide, but you can refer to my papers and you can look it up, like what 16 and 25 refers to. These are existing self-supervised method developed for audio. And we can see that as compared to, if we compare with existing self-supervised methods, our method works really well as compared to these old tasks. For example, if we look at this particular task or this temporal gap task, then this is around 64% or 66%, but we improve it to 82%, which is a huge jump. And we can also look at methods like Trill. I'm not going into detail, but this method is specifically developed for speech related tasks only. But even if we compare with this method, we have a very small gap between these two tasks. So this method is specifically developed for speech tasks, and we only compare it on the speech related task, and we are still very close in terms of that. But our model is on overall works really well across different type of tasks. So you can have one model that can do all these different type of tasks. So to conclude, the idea of self-supervised learning is to learn general purpose representations from any type of sensors which would be like audio or IMU or ECG, without any manual annotation from the humans, and we saw that we can get really good, really excellent performance on downstream tasks if we pre-train with self-supervised learning and we go on and we pre-train or we fine-tune on the task that we are interested in. So we can say that because these self-supervised tasks are very simple and straightforward to implement, or now they look like at least. So now we know that they have very excellent generalization property that they can, for example, if we train on audio set, they transfer really well to acoustic scene. So now we know that, okay, this thing works. We can use similar methodologies for lifelong learning. For example, we can deploy these type of solutions, or we can put them up on the devices like smartphone or smartwatches or some other type of device like Alexa or related devices, and they can like constantly listening or constantly sensing about what you are doing in the environment, and then they can like keep developing or keep learning on the fly because you don't really need to intervene for the learning part. But the important point I would like to mention is that we need to be very careful when we develop these type of self-supervised tasks, because these neural networks, we are still trying to understand how these model works. There is the neural network interpretation or interpretability in general is a very hot area of research. There is a tons of work going on in that area. So the thing is that these neural networks are very, they try to find shortcuts to basically solve the problem. So we need to be very careful when we try to develop self-supervised tasks, so that the network only looks at semantically meaningful aspect of the input as compared to just finding some stupid type of correlations that don't really generalize well. But the thing is that this is not really related to self-supervised learning. This is really related to learning with fully supervised models as well. You can take a look on this paper to find out more like what is shortcut learning and how network bias toward texture and other type of features in the images. And now I will briefly like to mention a few points what you can do today about this entire thing. So the one thing that is really important, and I wish I would have I paid a lot of attention to it, but I would have paid more attention towards it, is that you really need to work on your fundamentals. If you want to do any type of research, or if you want to work as a very good engineer, as a software engineer, you want to go on become a research engineer, you need to get your fundamentals right or straight. Like you need to have a very nice background in statistics and optimization and linear algebra and also data structures. In addition to this, you can develop this habit of learning research articles. You can look up online and find like there are tons of material surrounding this idea on how to read well a research article or a scientific paper. This is a really good skill to have as an undergraduate, or even when you are doing your master's. You have plenty of time. So even if you read one paper in a week or over the weekend, and if you try to accumulate how many papers you read in 2 months or 3 months, then you will look back, you will be really happy that you developed this habit and how many papers you have read and how many new things you have discovered or learned. So this is really nice. I highly recommend it that you should develop this habit or like this skill of reading research articles. The most important thing when you develop this habit of reading research paper, or you develop this skill, is to identify key priority areas, especially related to Pakistan. I'm feeling a bit sad, and I don't know, like sorry as well. I don't see a lot of Pakistanis when it comes to research and stuff like that on a global scale. I'm very sorry to say this, but we are nowhere close. So we need to do better as compared to our neighbors. So there are key areas of focus where we need to put our effort, which I think are high priority for us. Like for example, for deforestation, we can develop these type of models from satellite imagery where we can identify, okay, like we planted these trees here, but now they are not here anymore, or someone is cutting them down or stuff like that. We can develop methods for medical imaging, like we can help aid our doctors in quickly going through many of the patients, like or scanning their x-rays or stuff like that, or their MRI scans and stuff like that. We can develop tools to help them better make diagnosis. Another important area I believe is that we need to have methods so that we can detect fake news or disinformation. And same goes for finance or fraud detection in banks and in general on in any e-commerce website and stuff like that. Another key, if you are not interested or you think that, okay, this is out of my reach, what you can do is you can help curate data sets specific to our region. For example, you can curate a data set of audio related to Urdu, where people are speaking Urdu and they are like talking to each other. For example, there's some music playing in the background, or there's some other stuff going on. You can curate these type of data sets, which is going to be really useful for the community. And not a lot. So people in Pakistan and some part of India, people speak Urdu, and not other people who are doing research in these areas speak Urdu, so they don't put any effort, or it's not in their to say that it's they are if they label these type of or develop these type of data sets, it's not in their favor. So we need to take up this responsibility to curate these type of data sets. And so basically coming back to that other point, that for example you can curate data sets so that others can use, so the people who are doing this research, for example in self-supervised learning or unsupervised learning or in different type of settings, they can use these data sets, and then it will help us as well in the end, because if someone is making a model for recognizing of keywords or hot words, and they use the data only from one particular region, let's say from India, because it's a big market, and then that model is not really going to work directly for us. So we need to take this initiative. We need to curate small, nice data sets and make them big over the time and make them available for researchers to use. Thank you so much. These are my contact address if you guys want to contact me. If you guys have any question about the work or in general, I would be very happy to do that. Thank you so much.
Thank you, Aqib, for this wonderful presentation. I hope the people have bombarded with a lot of information about what's going on, the state of the art in the supervised learning.